Okay, welcome everyone to the robust optimization webinar after some short break over Easter. So I'm very happy to have Soroosh Shafiee here today. He's an assistant professor at Cornell University. Before he worked at Carnegie Mellon and ETH Zurich, besides other universities. And he's working on decision making, especially optimization under uncertainty and optimal transport. And he received already the NSF Career Award, besides other awards. And I'm very happy to have you here. Please.
Yeah, thank you so much, Yanis and Ahmad for giving me this opportunity to present here. So today I'm going to talk about a topic that I'm actually working on more and more these days. So it's about learning or decision making when you actually face both local and global adversarial corruptions. I will explain what I mean by global and local corruptions in the few next slides. But this is actually a joint work with my colleague from Cornell, Ziv Goldfeld, from EC department, and his previous PhD student, Sloan Nittert, who is now at EPFL doing a postdoc. So I'm going to show few animations during my talk. All those animations are thanks to Sloan. Also, most of the proof, all the proofs are thanks to him. And if you have any question, technical question from that, please reach out to us. Good. So with this introduction, let me just briefly tell you a little bit about learning or decision making in the abstract sense. So throughout my talk, I'm going to model uncertainty or data using a random variable z, whose probability distribution is described by P. In decision-making problems or in a stochastic programming literature, we would like to find a decision theta p that minimizes the expectation of some loss function n, where the expectation is taken with respect to this distribution p. So I'm going to denote by the solution of a stochastic programming problem by theta p. Unfortunately, in many real-world applications, this distribution p is rarely available, and at best, we have some IID samples from this distribution. In this data-driven world, we would like to then come up with data-driven decisions, which I denoted by theta hat, that in a way minimizes what is called the excess risk. So the excess risk of the decision theta hat is essentially defined as kind of a regret. So what is the expectation of the loss under my decision? Minus the best that I could have done in hindsight if I know the distribution P. So as you see, just minimizing excess risk is as difficult as solving the stochastic optimization problem because we don't know this distribution P, but there are good estimators in stat literature that are so-called minimax optimum, which means that this is really the best that you can do given the data that you have. So one of such estimator is sample average approximation, where it's a very simple. So just use your data, replace P with empirical distribution, and solve the stochastic programming problem with this empirical distribution. Maybe surprisingly, this is known to be minimax optimal under several different cases. Okay, now let me just switch to a different topic. In many real-world applications these days, it's kind of unrealistic to assume that we have data that are clean. In fact, in many recent applications, the data is attacked by an adversary, which means that we don't really observe clean data. And in the literature, there are two types of contamination models that are based on the type of attack that this adversary can go with the data. They are branched in two different types. So the first type is the local corruption model. So I'm going to present this model in the simplest form. So under the local corruption model, the data that we observe are drawn from a locally perturbed distribution, but the learning tasks remain the same. So given this corrupted sample from this corrupted distribution, I would like to still make data-driven decisions theta hat, that minimizes the excess risk relative to the solution of a stochastic program with respect to the clean distribution, the green one, not the red one. So it's known that regularization is actually very effective under this scenario. In fact, the regularized ridge regression problems can be actually minimax optimal under certain scenarios. Another principal approach is robust convex optimization, which tries to say that given the data that you have, you construct uncertainty set. In the simplest case, let's say it's a ball around your data points and you take all these balls. Let's say it's a ball with radius rho, and then you solve a minimax optimization problem to essentially minimize the worst case possible realization. And you get a decision, and this actually also known to perform very well under local corruption. So if I go to the literature of machine learning, this is very closely related to the so-called adversarial learning framework, where people observe that by just adding a little bit of noise to some data that we have, we can actually get some completely arbitrary output. And practitioners also observe that by training neural nets with this min-max approach, they can actually reduce the sensitivity of network to such errors. So a more principled approach that captured robust optimization and regularization as a special case is the so-called distribution robust optimization. So I'm going to focus on these models that are constructed from optimal transport. The whole idea is that given the data that we have, we construct an ambiguity set. It's a set of distributions that could have generated the clean data with high probability. Then we solve this minimization, min-max optimization problem that essentially wants to minimize the worst case expectation over all distributions that belong to this ambiguity set P. We actually prove that this approach is minimax optimal if you have actually local corruptions. Okay, now that I just tell you what is local corruption, let me switch to a completely different model, which is the so-called global corruption model. So under global corruption, some of the data that you observe are completely arbitrary. But given this arbitrary data is usually called outlier data. So given this data set that is corrupted by outliers, we still want to make data-driven decisions theta hat that again minimizes excess risk with respect to the solution of a stochastic programming problem with clean data or clean distribution. So this is the topic that people traditionally studied in robust statistic literature. The biggest open problem in robust statistics is more or less computational. So the statistical side is fairly well understood, but the main remaining problems are really about scalability or algorithmic scalability of these type of problems. So Huber was kind of disappointed about algorithmic development of robust statistic problems. At the conclusion of his book, he wrote that it appears to me that none of these methods are really scalable. And if you want to get a solution, it's the best if we just go with heuristic. And we can only just find solution under special cases. So there is no hope to solve these problems for more general situations. So this was kind of the thing for many years. And the consensus was that these type of problems are very difficult to solve, and they lead to formulations that are intractable. In fact, it is known that DRO badly fails in the presence of outlier data. And this is kind of easy to see because DRO is a robust approach, is a conservative approach. And by solving a min-max problem, you even give more weight to outlier data. Therefore, instead of fitting to your clean data, you fit more to outlier data. So an alternative to DRO is what is called distributional favorable optimization, where instead of solving a min-max problem, you solve a min-min problem, and you minimize the minimum expected loss over all distribution in this ambiguity set. And intuitively, this makes sense because it essentially reduces the weight of the outlier, and you just give more weight to the inlier data. Unfortunately, this mean-mean approach leads to non-convex and non-smooth optimization problems. You can actually, find or develop first-order optimization algorithms to converge to a stationary point of these mean-mean problems. The issue is that you usually converge to a stationary point that you don't really know if it is min-max optimal or not. So you lose the statistical side. You can actually focus on a statistical side and reformulate those interactable optimization problems as a mixed integer linear programs or conic programs. The issue is that this approach is not really scalable because we know these problems are NP-hard. So in the worst case scenario, you actually need to explore every possible scenario, possibilities, and therefore you don't get a scalable algorithm out of this approach. So given all these failures, there are actually some good news. More or less recently, we learned that for class of robust statistic problem, you can actually use very efficient algorithms to get minimax optimal estimator and also ensure tractability. So there are essentially two ideas in this literature. One idea is about using robust statistic measures, like instead of using mean, you use median. So this leads to the SOS approach and semi-definite programming. But the better idea that is more tractable is just what people call the pruning idea, or removing data or cleaning data. So there are two approaches here. One is based on filtering method, and the other one is just to use first order methods to solve a certain non-convex optimization problems. So all in all, we fairly know that in many situations, we can actually get minimax optimal decisions based on these three different models. And let me just visualize one of them for you in 1D. So for example, assume that I have this data or distribution in the population limit that contains some outlier. So the idea of filtering in 1D is that you just cut epsilon fraction of your data from the left and the right tail, and then you work with the remaining data. And it's known that this is actually optimal, minimax optimal from the statistical sense. So this is really the best that you can do. So in the remaining of my talk, I will show you how this filtering algorithm or filtering idea can be extended to high dimensional setting. Because in 1D, it makes sense to talk about the tails, but in high dimensional, the notion of tail is not really well understood or well defined. Good. So with this kind of long introduction, I'm ready to tell you about the setting that we consider in this work. So I'm actually interested in learning under both local and global corruptions, but the learning task remains the same. So I would like to find data-driven decisions theta hat that again minimizes excess risk relative to the solution of the true stochastic program with respect to the clean distribution green P. So here is kind of a spoiler of the proposed approach that we have. So given this corrupted data, sorry, there was a question? Okay. So given this corrupted data, I'm going to just, in some sense, attack this problem in two phases. In the first phase, I clean the data, which means that I want to remove the outlier from the data or the global corruptions. Then to deal with the local corruptions, I'm going to rely on DRO. So in some sense, I'm going to merge the ideas from robust statistics and robust optimization to get a decision that is min-max optimal. Okay, so here is the agenda of my talk. To make things formal, I will talk a little bit about optimal transport and tell you what notion of optimal transport we use for this project. Then I formally define my corruption models, which is not about the population model, but it's more about the sample and adaptive adversary. After that, I'm gonna propose 3 different solutions, all of which are minimax optimal. And out of them, I will focus on one, which gives me a tractable reformulation or tractable algorithm out of that. Good. So let me start with the first part of my talk, which is about the optimal transport background. By the end of this part, I just hope that we get a good measure to kind of find what is the value of the corruption level under different scenarios. So as I said, I'm going to rely on the optimal transport definition, which dates back to the Kontrovic in the past century. So Kontrovic was interested in just transporting probability distribution from one location to the other one. And the formulation that he used was saying that if I just consider probability mass at one location in one distribution, I would like to transport it to several different locations. But I would like also to do this for any location in the distribution that is green. Therefore, I can just write a stochastic optimization problem that gives me the best transportation plan. So mathematically speaking, if I have 2 distribution P and P prime, I will solve this stochastic optimization problem that you have here. And the optimal value of this stochastic optimization problem gives the optimal transport cost between these 2 distributions. So as you see here, I have a function C that essentially measures how much cost I pay if I move unit probability mass from the location Z in the distribution P to the location Z prime in the distribution Z prime. Okay. So one important instance of optimal transport is the so-called P-Wasserstein distance. So what you do is that you take the norm of the difference between Z and Z prime, raise it to the power P, takes the expectation with respect to the joint distribution gamma, and after that you take the power to the power 1 over P. P-Wasserstein distance is very important because it's just a metric for probability distributions with PS bounded moments. But at the same time, it's also a special case of optimal transport because if I just set the transportation cost C to norm raised to the power P and then take this as optimal transport cost, and then after that raise it to the power 1 over P, I just recover the P-Wasserstein distance. Okay, so since I'm using norm, I can actually encode geometric information, and therefore this is actually a perfect metric to measure local corruption levels. Okay, so now let me switch to a different instance of optimal transport. The second instance is the so-called total variation distance, which is essentially half of L1 norm between 2 distributions or minimum mismatch probability between 2 random variables that follows the distribution P and P prime. Again, if I just use the definition of optimal transport cost, it's very easy to see that TV is an instance of optimal transport cost if the transportation cost function is the indicator function of Z not equal to be Z prime. Okay, so since there is no notion of norm or geometry in total variation distance, this will be a perfect metric to measure global corruption. Good. So now that we just see what is a good metric for just measuring local corruptions and global corruptions, I want to just get a combined metric that can actually give me a good sense of what is the measure of both corruptions at the same time. For this purpose, I'm gonna just rely on a notion that recently introduced in the literature. It's called outlier robust Wasserstein distance, and the idea is pretty simple. So, the idea is that given two distributions that I have, I'm actually allowed to remove epsilon fraction of the distribution from green and red distributions. And after I remove that, I just find the optimal transport plan to just move the remaining map. But as you see, so I need to just not solve one optimal transport problem. I also need to come up with the optimal pruning idea. So mathematically speaking, I just need to solve this complicated optimization problem. So I don't want to tell you more about why I'm solving this. But all I want you to remember is that because I jointly optimize over transportation plans and also the pruning strategy, I may face some sort of bilinearity. And because of that bilinearity, I may also face interactability if I use this particular metric for my decision making. Yes, this metric is great because it actually combines both local and global corruptions. But at the same time, whenever I'm using it, I need to be careful because I may lose tractability. Good. So now that we learn about all these three different notions of corruption metrics, now let me just tell you more about the corruption model that we consider in this work. So we are going to assume that there are some unknown IID clean data, Z1 to Zn, that are drawn from the distribution P. It's unknown, but they exist. And I'm also going to assume that this distribution P belongs to some class of distribution, which I denoted by G. And I call this G is the class of clean distribution family. So if you go to the literature of robust statistics, this is a very standard assumption. And G can be, different sets. For example, the set of all distributions with bounded second moment, the set of distributions that are Gaussian, the set of distributions that are sub-Gaussian, and so on and so forth. So throughout my talk, I'm going to assume that the clean distribution G is the set of all distributions with bounded variance. But because I don't want to just work with general sigma, I just also set that general sigma without loss of generality to the identity matrix. Okay, so given this setting, I can now formally define what is the adversarial model that I consider. So I'm going to assume that the adversary can see, it's an adaptive adversary, can see these clean distributions, clean data. Then the adversary start attacking these data. In the first phase, the adversary just locally corrupt the data, but the average amount of corruptions measured by some norm should be bounded by parameter rho. So this is the information that I have is that this average corruption should be smaller than rho. Now, if I use the definition of one Wasserstein distance, I can easily conclude that the Wasserstein distance between these two data sets or the empirical distributions constructed by these two data sets will be atmospheric. Okay. So the first piece of information that I have is that I know kind of this corruption level exists. Then the second phase of attack starts. The adversary just replace epsilon fraction of the data with completely arbitrary data points. So they first remove it and replace it. Now, if I again use the definition of total variation distance, I can actually easily conclude that the total variation distance between the orange and the red data set will be at most epsilon. Okay? Now, if I compare this red data with the clean green data and use the definition of epsilon 1 Wasserstein distance, I can easily conclude that the distance between the red data set and the green data set will be at most rho. Okay? So the great thing about this adversarial model or corruption model is that it doesn't really matter if the adversary first locally corrupt or globally corrupt. At the end of the day, this bound that epsilon Wasserstein, 1 Wasserstein distance between red and green data is smaller than rho still holds. Okay? Good. So what is the available information that I have as a decision maker? So I observe this, what I call rho epsilon corrupted data, so the red data. I know that there are some corruption levels in the local sense and global sense. In the local sense, I know the corruption level is rho. In the global sense, I know the corruption level is epsilon. And all I know is that there are some clean distribution that I don't know what is that. But all I know is that this clean distribution should be relatively close to the data that I observed, the corrupted data that I observed. And the closeness here is measured by this epsilon robust von Wasserstein distance. So I know this distance is at most. So given this information that I have, I would like to answer this simple question. Can we efficiently learn under this scenario? And by efficiently, I mean two things. Minimax statistical optimality, which means that is it really the best thing that I can do given the data that I have? But more importantly, I would also like to talk about computational tractability, because I don't want to propose an estimator that is not possible to compute or solve. Therefore, my goal is just to address both computational and statistical side at the same. Great. So, so now that we understand what is the setting and what type of problems we are looking for to solve, let me just propose three different solution approach, all of which actually gives you minimax statistically optimal solutions. And we will see that out of these three, one of them is actually gives a tractable formulation, and I will focus on that. Good. So the first attempt that we made to solve this problem just purely tries to use ideas from robust statistics. So what we consider is just to kind of like come up with a distribution estimation problem that handle both local and global corruptions at the same time. Clean the data, I get a clean distribution Q hat n. And after that, I just solve a normal stochastic programming problem with respect to this clean distribution Q hat n to get a decision. So we show that this approach is actually can give you a minimax optimal decision if the data cleaning procedure is minimax optimal with respect to this epsilon robust von Wasserstein distance. Okay. But if you remember, I told you that whenever you use this epsilon robust Wasserstein distance in your computation, you some sort of intractability. And this was actually the case. So because I use here for distribution estimation problem, I face intractability, and therefore I couldn't get something tractable out of this approach. So the second idea that we try to use is just to completely abandon the ideas in robust statistics and just use ideas from robust optimization literature. The proposal is very simple. So you just solve a DRO problem with respect to some ambiguity set. And we show that if you construct this ambiguity set in a good way, you can actually attain minimax optimal solutions. And the construction of ambiguity set is also not super difficult. You just use all the information that you have. So you know that this distribution Q should be a clean distribution, so it belongs to the set G. And you also know that the distance between this distribution Q and the corrupted data that you observe with respect to this epsilon Wasserstein, one Wasserstein distance should be smaller than rho. But again, the same issue appears. Because I'm using this epsilon robust Wasserstein distance, I get again this bilinearity in my reformulations, in my DRO reformulations, and therefore I get a non-convex optimization problem, which we don't know how to solve in polynomial time. Then we reach to the third proposal, that is actually what I showed you earlier. It's based on first cleaning the data so that just I remove outlier. So I don't really care about the local corruption. Then I get clean distributions that doesn't have any outlier. I just solve then a DRO problem using this data with respect to some ambiguity set. And I can show that this is minimax optimal if I construct this ambiguity set using one Wasserstein distance. So this is the biggest important distinctions. Instead of relying on this epsilon robust one Wasserstein distance, I just want to change it to one Wasserstein distance. And the reason is that we actually have a very good understanding of DRO problems with Wasserstein ambiguity set. It's known that this type of ambiguity set gives you a very good tractability results. And the only remaining part that I need to care is that what should be the notion of minimax optimality for the data cleaning approach. Okay, so previously I used this epsilon robust one Wasserstein distance leads to interactability. Now I'm going to show you that if I again use the one Wasserstein distance for my data cleaning approach, I can actually get something that in the end will be tracked. Okay, so this is what I want to do in the remaining talk. The remaining part of the talk. So I'm not talking so much about the DRO part. I will focus on the data cleaning. And I'm going to tell you how you can actually get something tractable out of this minimax optimization problem. Good. So let's just focus on the data cleaning procedure. As I said, I'm going to assume that I have these red data sets, the raw epsilon corrupted data. And given this data, I would like to find an estimator or a distribution Q hat n that is minimax optimal with respect to one Wasserstein risk. So these can be formulated as these min-max optimization problems that I show here. So you would like to minimax optimal with respect to all clean distributions that belong to this G. But this optimization problem is very difficult to solve. And in a statistics, when they want to talk about minimax optimality, the first step is that we need to see what is the dependence of this object in terms of the corruption levels, epsilon and rho, and the underlying dimension of the uncertainty, D. So the first step for all these things was just to see what is this dependence. And we show that this dependence will be in order of a square root of D times epsilon plus rho. Okay. So now that we know this dependence, we can actually just use different estimators and see if they match this kind of rate, this square root D epsilon plus rho. If they match, the estimator is minimax optimum. So this is kind of, you don't solve this min-max problem exactly, but up to some constant, you get the best that you could do asymptotically. We also have a non-asymptotic version in the paper, but I thought for the presentation, it's the best if I just focus on the asymptotic version. Good. So the first estimator that you can come up with, and this is the kind of the easiest thing that you can use, is just very naive, just use the empirical distribution on the corrupted data. And you just say that, okay, this is my estimator. So maybe surprisingly, people in optimal transport literature show that this is minimax optimal if you just have local corruptions or epsilon, the global corruption level is equals to 0. Uh, but it's very easy to show that as soon as you have both local and global corruptions, the von Wasserstein distance between this estimator and the true distribution P will be infinite. So this estimator is infinitely bad for the task that I have. So the second idea is just to go to the robust statistic literature and just see what estimators are there. And if you just search there, there is one big class of estimators that are known as iterative filtering methods. So in this type of filtering methods, we would like to find a distribution Q hat n that minimizes this that solves this optimization problem. Just let me just talk a little bit more about this optimization problem in more details. So the objective function of this optimization problem is the largest eigenvalue, the positive eigenvalue, that plus is for the positive part, of the covariance matrix of Q minus identity. So why do I care about the largest clipped covariance matrix? The reason is that if you remember, I just assumed that the clean distribution family has this, the covariance of distributions there has this upper bound identity. Therefore, by minimizing this objective function, I make sure that all eigenvalues of sigma q is smaller than 1. And therefore, I get something that is clean. Okay, so the decision variable in this minimization problem is a distribution Q that is kind of close to the corrupted data, but in TV sense. So I'm not going to use any information about rho, but I just focus on epsilon. So the TV distance between Q and P hat, the P tilde n, the corrupted data should be smaller than a constant times. Okay, so as you see, throughout this formulation, I use epsilon and the information about the clean distribution family G. Okay, so this is actually known to be minimax optimal if there is no local corruption or rho equals to 0. But we show that if you have both local and global corruptions, you get this asymptotic rate of a square root of d epsilon plus d rho. And as you see, there is this bad dependence on the dimension d when you have this local corruption. Okay, so I'm gonna next try to find an approach that just get rid of this d and hopefully replace d with some constant or ideally 1. So this is the theorem that we have in the paper. And we show that if we just slightly, a little bit, change the objective function of this iterative filtering algorithm from lambda max to trace plus, you can actually get a minimax optimal estimate. Okay, so let me a little bit talk about the objective function in the new problem. So previously, when I had lambda max, I only care about the largest eigenvalue that was larger than 1. So now the main difference in my estimator is that I don't only care about one eigenvalue. I want to penalize all the eigenvalues that are larger than 1. Okay, so it turns out that if I only care about the largest one, I pay the price, which means that I have this dependence, bad dependence on the dimension d. But when I just in my optimization problem care about all eigenvalues larger than 1, I can remove that bad dependence. Okay, so you may also ask me if it is possible to get rid of this dimension d and just replace it with something smaller. It turns out that this is also possible in 2 scenarios. So the first scenario is that if your true covariance distribution, sigma p, is low rank and has rank k, or if your inference task, your loss function, is kind of low rank, which means that when you solve the stochastic programming problem, the rank of this distribution theta p, this decision theta p, when the loss function is defined through a linear map of theta transpose and z, is at most k. So if the rank is at most k, which is smaller than d, under this situation, we can also show that if you replace trace, which penalizes all eigenvalues, to this function sk, which penalizes only the k-th largest eigenvalue beyond 1, then this estimator becomes a minimax optimal, and you can replace d with k for this estimate. Okay, so two very important examples here is that if you just think about mean estimation problems or linear regression, k is typically 1, therefore you don't have any dependence on the dimension t. Great. So in the remaining time, let me just briefly tell you a little bit about the proof idea and how we show this result. So the idea of this proof is based on what is called the minimum distance estimator. And in the statistics, it's known that this type of estimators can achieve the best possible results. So I'm gonna just focus on one of those, which I call it Q hat MDE, that minimizes the two Wasserstein distance between the distribution Q and the set of all distribution, all clean distribution family G. So I show this clean distribution G with this kind of half ellipsoid. Then I have a distribution Q. Then I observe some corrupted data, P tilde n, which is not clean, which means that it's outside the set. So what is this QMDE tries to do? So the feasible set is a ball around this with respect to total variation distance. Then it tries to find a distribution that is closest to this distribution family G with respect to two Wasserstein distance. So it's kind of like this distribution. Okay. And we show that if you just compare the one Wasserstein distance between this estimator and the true distribution P, it's in the order that I wanted to be in. Okay. So so I kind of solved the problem. But the issue is that as you see, this Q hat MDE is not in G, so it can be outside. Okay. And therefore it means that I need just to kind of find a solution that works for me. So I cannot just rely on Q hat MDE. So what we showed is that if you just a little bit explore this set, and instead of having G being the set of all distributions that the covariance matrix is smaller than ID, it is smaller than 2ID, then you can actually do a lot of things. In particular, we show that the W2 distance between Q and G is kind of upper bounded and lower bounded by these two quantities, one with respect to ID and the other one with respect to half of 2ID. Then using some sort of sandwich argument, we show that this W2 distance between Q and the clean family G is kind of in the order of trace of sigma Q minus identity plus. And if I use this instead of W2, I get a theorem that I had. Okay. So one idea that I want to mention is that you may ask me why I use W2 instead of W1 for this distribution estimation task. The main reason is that if you think about my clean distribution family G, it's a set that is with respect to second moment information. So it just restricts the covariance matrix. Unfortunately, if I just rely on one Wasserstein distance, I can only change the first order moments. And I cannot really have a good grip on the second order informations or second moment order informations. And because of that, I had to switch to W2 when I want to do the distribution estimation. Okay, so now that we see that we need to solve this optimization problem to get an estimator, let me just tell you a little bit how to solve this problem in kind of a tractable fashion. So, okay. So the first thing that I want you to realize from this optimization problem is that the objective function has some sort of a good properties. Uh, it's a non-convex problem, but we know that the objective function is always larger than zero. So the best loss function that I can get is zero. Okay? And if I'm at zero, then I'm optimal. Okay, so this is the good news. There are ways to solve this optimization problem, therefore, to the optimality if I make sure that I get in the end something that gives me zero loss. So I'm going to show you kind of the simplest implementation here, but I believe this sort of idea can be easily extended to gradient-based method. So what you see here is kind of two ellipsoids. So one is a red ellipsoid, which, as you see, it's the covariance matrix of the data that is corrupted. The second ellipsoid is not really a ellipsoid; it's just circled or just high dimensional circle. And this is kind of ellipsoid defined by the identity matrix, and just it's the set of all distributions whose covariance matrix is smaller than the identity. So clearly my distribution is not clean. Therefore, in some directions, I'm outside this clean distribution family. So the algorithm is very simple. It just tells me, find those directions, project your data to that directions, okay, that subspace, then randomly remove the data based on the distance on from the center of this circle. Then you remove that data and you project back into the high dimension, and then you repeat this process. Again, find which direction you go outside the unit circle, and then you repeat and repeat and repeat. So what we showed is that if you repeat this procedure, you can actually converge to the optimal solution or the optimal value of this optimization problem, zero cost, in polynomial time. We also show that this cleaning procedure is guaranteed to remove more outliers than inliers, which means that we can also for sure guarantee this algorithm converges. So let me just do a quick recap of what we see. So as I said, I assume that there are some clean data that is unknown to the decision maker, but the adversaries see those data, first locally corrupt the data and then globally, or the other way around, doesn't really matter. We see that the proposed solution that we had was kind of to first clean the data to get rid of the outlier, and to deal with the local corruption, we rely on robust optimization technique. And we formulate a DRO problem with one most certain distance that can be used to solve this problem. Okay, so what are the open problems for this kind of research topic? So the first open problem that just keeps bothering me is that I assume that I know the corruption levels epsilon and rho throughout my talk, and my algorithm actually use this information. So it's the best if I have an algorithm that doesn't rely on this type of information. And I know there has been some work in robust statistics by Donoho and some recent work by Yanis and Bart that tries to address this issue for just the purely robust statistic problems. And I think those ideas could be potentially used for this problem, hopefully. The second thing that I want to mention is that the tractability results that we achieve is kind of restricted to the bounded covariance family G. It's better if we actually can extend these results to the class of sub-Gaussian distribution, for example, or Gaussian distribution, because for these classes, we can actually get even sharper bounds. There is also a very important connection between adversarial contaminations and other settings in statistics. One of them is heavy tail data, and the other one is differential privacy. So for heavy tail data, the corruption that you observe is not adversarial, it's part of the distribution, it's stochastic. But still, you would like to, depending on the task, you would like to kind of ignore that heavy tail, or sometimes you want to optimize for heavy tail. So depending on your task, you need to be very careful what type of method you use. And I think optimal transport actually provides a very rich framework to address both adversarial contamination and heavy tail data. So the other important topic is differential privacy, where again, you corrupt your data. So if I just have some data that I want to hide the identity of certain people from that, again, I inject noise. So I corrupt the data. But the nature of corruption is again different. So it's not adversarial. So it's a corruption that is used to preserve some sort of privacy of users. So the purpose of that corruption is not adversarial, and therefore using DRO for that doesn't make so much sense unless you are very careful with respect to the design of your ambiguity set. So again, good news is that optimal transport offers good metric for handling differential privacy concerns. So the last part that I want to mention is that there is a natural extension of this framework to online problems, where instead of just having all the data in batch, you just see the data one by one. But this adversary can just locally and globally change the data throughout the process. So the problem is very challenging, but I believe this can be solved as well, and we are working on that. But the more important problem, in my opinion, is the dynamic setting, where you have an underlying dynamical system, and when you just do, for example, measurements from this system, you may have outlier data, and you also have measurement noise. So therefore, this classic Kalman filtering algorithm, or LQR, LQG controller, is not really designed to handle outlier data. It's just for local corruption. So the question here is that, can we do something? Can we actually get some better estimator in these settings, or better controller in these settings, and so on and so forth? So with that, I would like to stop, and I'm happy to take any questions that you have.